This presentation is on DDR2 and 3, and we'll be investigating many aspects of DDR2 and DDR3 and how our controller works with regards to DDR2 and DDR3. The agenda for this presentation is sectioned basically in two sections. One, we would discuss the basic DDR SDRAM, and we'll just talk about the organization and how the signaling works and how the read and write timings are organized. And on the second portion of this presentation, we'll discuss how the memory controller in PowerQuake and Core IQ will operate with DDR, and what are their features and capabilities working with DDR2 and DDR3. So the first section would be discussing the basic memory organization. Here you see a schematic representation of a single memory cell. The central portion to this memory cell structure is a storage capacitor. It's a very weak and leaky capacitor. One side of this capacitor is connected to VCC/2, and the other side would store the logical value depending on the charge being VCC or ground. The transistor that is used in here is an access transistor to allow the charge that is stored in the capacitor to flow to the other side, which is called the column line. So the transistor is turned on by the gate with using the row line, and the information is transferred to the column line. And the column line to store to read the value that is stored on the capacitor, the row line is activating the gate of the transistor, turning on the transistor, and allowing the charge from the capacitor to flow on the column bit. Before the transistor is turned on, the column bit is pre-charged to VCC/2, and the line is momentarily removed and left floating. However, the parasitic capacitor on the parasitic line capacitance will keep the charge or voltage that is on the line, and when the read voltage, the charge on the capacitor will influence either increase or decrease the VCC/2 voltage on the column line. That change in voltage is sensed by sense amplifiers or sense amps, and they'll store in a row buffer. So a single memory cell is not sufficient. They are organized in row and column fashion, as you can see it. It's a two-dimensional array. The address that is going to locate the memory location is sectioned in two parts. It's decoded into rows and columns. So when a row is selected, all the transistors that are on that row will be activated. Hence, by activating a row address, all the information on that row will be transferred by sense amplifiers into the row buffers. However, the organization of this two-dimensional array is limited, as the number of rows and columns cannot be increased indefinitely. To increase the memory size, we add more of these two-dimensional arrays, and we call them banks. And the other advantages that this would have is that while operating on one bank, it could also simultaneously work on other banks. So it will increase the performance of the memory. The operation or accessing a memory is always starts by an active command taking the information that was in the two-dimensional array into the row buffer. Once the information is transferred into the row buffers, the information is no longer available in the two-dimensional array or bank 1 as it's depicted here. Next, to do any read or write operations, the column address of where to begin reading that information from the row buffer is provided, and all the read and write operations happen on the row buffer itself. Once the information has been read or written to, and we no longer need the row buffer, we close it, or it's called, this action or this command is called a pre-charge back, so the information is restored back into the two-dimensional array. Here you see a single SDRAM. It's a DDR2 SDRAM, and in addition to information provided in this slide, I'd like to point out that there are two memory banks, or there are two memory bus that I'd like to point out here. One is the address bus, which consists of the DQ or the byte, and DQS or strobe, and data mask or DM. All these signals operate together as a bus, independent of the other signals. The other signals, which are address, command, and control signals and clocks, operate as the other bus, which is called the address and command bus. The address and command bus is signaled or sampled by the clock signal, rising edge of the clock signal, and the data bus is sampled by rising edge and falling edge of the strobe. A single byte of memory is not sufficient, so they are organized in a concatenated fashion to increase the number of bytes in a memory. There are 60, here you can see a 64-bit bus, which consists of 8 byte lanes and an additional ECC byte lane. And as you can see, all the address and command bus are all connected to all the SDRAMs to the same locations. The only thing that is different here is between connections for these SDRAMs are the byte lanes. The order of the byte lanes, as you can see, they are different. Here is a basic chart of commands, and I like to point out that the commands that are sent to SDRAM are all active low. Here we have chip select, row active select, column active select, write enable, and they are all active low. In an active command, we want to open a row. So we select the chip select that we want to access, and the row access select is pulled low to indicate that we are going to select a row from the memory. And as you can see, the read and write commands, they have the column access select low, meaning the operations of read and write occurs on the column, or once the memory has been the information in the memory has been passed into the row buffer. The pre-charge or closing of the row buffer is, again, it needs to access what row put that information back in there. So we have the row access command activated low here. And you also have precharge all and refresh commands here for your reference. Read and write occurs in bursts. They do not happen in single byte reads or single byte writes. It happens in burst, and the bursts are the information that is provided for the read and write is the beginning address of that burst operations. There are 4 beats or 8 beats of transfer of data every time, depending on what the memory selection allows for 4 bursts or 8 bursts, or if both burst types are